A single star pulses in a galaxy 72 million light-years away. James Webb watches it, waiting for it to cheat, waiting to fake the number that would rescue physics. It doesn't. It obeys. And in that quiet obedience, Adam Riess sees the crack now running straight through modern cosmology itself. That obedience is what this whole story turns on. Two of the most trusted telescopes ever built now agree on a number the universe is not supposed to give us. Adam Riess, the Nobel laureate who spent 20 years chasing every possible error, is telling anyone who will listen that the last convenient excuse just died, and that our entire model of the cosmos may be missing a piece we never suspected. Here is the mystery in one sentence. The universe expanding around you right now is expanding faster than the universe was supposed to, based on its own baby picture, and nobody can find the mistake. To feel why this matters, you need to understand a single number called the Hubble constant. Every meter of space between two distant galaxies is stretching. The Hubble constant is the exact rate of that stretch. It is not a speed. It is new distance appearing out of nothing, everywhere at once. That number governs the age of the cosmos, the fate of every galaxy, and the meaning of every photon reaching your eye. There are two ways to measure it, and they should agree. The first way starts with the oldest light we can see, the cosmic microwave background. 14 billion years ago, the universe cooled just enough for light to escape from a fog of hot plasma. That first light still surrounds us. The Planck spacecraft mapped it in extraordinary detail. From those tiny temperature ripples, physicists ran the standard model of cosmology, lambda CDM, forward through time. The model works. It predicts the pattern of galaxies. It predicts the ratio of hydrogen and helium. It fits the sky to a fraction of a percent. From that model, the expansion rate comes out to 67.4 kilometers per second per megaparsec. Precise, confident, almost boring in how well it fits. The second way ignores all of that. It walks up to the universe with a tape measure. I want you to picture a ladder. The bottom rung is close. The parallax of nearby stars, measured directly by the Gaia satellite as Earth swings around the sun. The next rung is Cepheid variable stars, the ones that pulse. Their pulses were connected to their brightness more than 100 years ago by Henrietta Leavitt, and that link still holds today. Time their heartbeat, and you know how bright they truly are. Compare that to how bright they look, and you have the distance. The next rung climbs higher, using type Ia supernovae, dying white dwarfs, whose explosions all release nearly the same amount of light, to reach across billions of light years. Rung by rung, the ladder marches out into the cosmos, and at the top of it, you read off a Hubble constant. Adam Riess and his JWST team have been sanding and resanding every rung of this ladder for 2 decades. When they finish, their number comes out to 73.0 kilometers per second per megaparsec. 67, 73. Look at those two numbers, a 9% gap. That does not sound like a crisis. It sounds like a rounding error. But at the scale these instruments now operate at, it's roughly a 5 sigma disagreement. The same statistical bar physicists use to call something a discovery. In practical terms, it means that at the size of a large galaxy, the universe you see is delivering millions of light years of expansion that the CMB says shouldn't be there. One universe, one physical constant, two measurements that refuse to shake hands. For years there was a comfortable escape route. The problem, some argued, wasn't the cosmos. It was Hubble's eyesight. The old Hubble Space Telescope has a pixel scale that gets soft at extreme distance. Cepheids in far galaxies live in crowded neighborhoods packed shoulder to shoulder with other stars. And if you can't cleanly separate one blue giant from its neighbors, some of their light bleeds into your target. The Cepheid looks a hair brighter than it really is. Distances shrink. The Hubble constant inflates. You get 73 for a reason that has nothing to do with physics and everything to do with photography. It was elegant, it was testable, and it was the last major defense between lambda CDM and a full-blown crisis. So Riess did the only honest thing left. He aimed the sharpest eye ever put in orbit, a telescope built to see through dust, resolve dying suns beside newborn ones, and split apart stars Hubble had been forced to blur together. Straight at the same Cepheids Hubble had measured. The James Webb Space Telescope opened its mirror. It focused on a Cepheid in a galaxy called NGC 5584, and it watched. Webb didn't blink. It resolved individual stars where Hubble had seen a smear. It measured the same Cepheids Riess's team had used for years in 5 different galaxies that host type Ia supernovae. If the crowding excuse was right, Webb's sharper images should have peeled away the extra light and pulled the brightness and the distance back into agreement with Planck's number. The measurements came back, and they matched Hubble within about 0.02 of a magnitude, a margin so small it might as well be 0. Read that again slowly, because it's the moment the argument changed. The stars behaved exactly the way Riess had said they behaved. Not slightly, not mostly, exactly. When the JWST team ran the statistics, they were able to rule out crowding as the source of the tension at 8 sigma. 8. That's not a rejection, that's a burial. The escape route was gone. Now the ladder itself is under a microscope, and every rung still holds. Gaia's parallaxes are solid. The masser in NGC 4258, which anchors the distance scale directly from geometry, is solid. The Cepheids pulse the way Leavitt said they would. The supernovae look the way they should. There is no crack in the tool. So if the number is wrong, the number is wrong because the sky is wrong. And then a second team spoke up, a team that a lot of people expected would sink the whole thing. Wendy Friedman at the University of Chicago has spent nearly as long as Riess measuring distances, but with a different philosophy. She and her Carnegie Chicago collaborators like to sidestep Cepheids entirely, using 2 other kinds of stars, the tip of the red giant branch, and the peculiar carbon-rich stars physicists nickname JWST. Different rungs, different assumptions, a completely independent check on the top of the ladder. The result, using their own JWST data, came in around 70, lower than Riess, a quieter number. Some headlines briefly claimed the crisis was solved. Then someone did the math. 70 is still not 67. Friedman's supposedly conservative measurement is still sitting above Planck by more than 2 sigma. She and Riess disagree on how to select which host galaxies to trust and which to wait, a genuine methodological argument that will play out over years, but they agree on the thing that matters. Neither team can reach the CMB's number. The gap between the high and low answers is smaller than the gap between either and the early universe model. The rival didn't cancel the tension. She reinforced it from a different direction. This is the reversal. The problem isn't the ladder. The ladder is telling the truth. The sky above the top rung is a different color than lambda CDM said it should be. So the search turns outward. Maybe we live in a strange spot. Maybe the local universe just happens to be slightly underdense, a bubble a few 100 million light-years across, where matter is thinner and space is expanding a little faster than average. This is the local void idea. The trouble is that when astronomers actually map the galaxies around us, they don't find a void that big or that deep. The bubble doesn't exist at the strength you'd need. Same story for supernova drift. The fear that type Ia explosions in ancient galaxies behaved differently than modern ones. Every check tightens the constraint. Every check keeps the gap open. So the questions stop being about the measurement. They start being about physics. What if the universe, in its first fractions of a second, briefly had a burst of extra dark energy, a shove that faded quickly, but left the early cosmos in a slightly different state than Planck's model assumes? That's the early dark energy idea, and it fits some of the numbers. It also has its own problems with galaxy formation. What if dark matter and dark energy talk to each other in ways we haven't detected? What if there's a fourth kind of neutrino we've never caught? What if gravity itself, at the largest scales, isn't quite the equation Einstein wrote down? Each of these ideas fixes some things and breaks others. None of them has been confirmed. All of them exist because the model needs help. And then, quietly, from a completely different instrument, came the sound of the second shoe dropping. A telescope in Arizona called DESI has been mapping the three-dimensional positions of tens of millions of galaxies, using ripples frozen into their distribution from the infant universe. Those ripples are called baryon acoustic oscillations, and they are essentially a cosmic ruler laid across billions of years of history. The ruler shouldn't stretch. In lambda CDM, it doesn't, but in DESI's data, it seems to. The oldest measurement of cosmic geometry is telling the same story the latter tells. Dark energy may not be constant. It may be evolving. Two completely unrelated instruments, one counting galaxies, one climbing to Cepheids, have now both looked at lambda CDM and found it wanting. This is the moment the story stops being about a telescope. It stops being about Riess versus Friedman, or Hubble versus Webb, or one team's calibration versus another's. Two instruments that share nothing, not a mirror, not a method, not a target, have independently walked up to lambda CDM and produced results it cannot fully absorb. When that happens, you are no longer looking at a measurement problem. You are looking at a model problem. And the strongest surviving explanation, the one physicists are quietly circling with increasing seriousness, is the one that changes the meaning of Einstein's most famous mistake. He called the cosmological constant his greatest blunder. He inserted it into his equations to hold the universe still, then tore it out when he learned the universe was expanding. Decades later, Riess himself, along with two other teams, discovered that the expansion is not just continuing, but accelerating, and the constant came roaring back to explain it. That is dark energy. It has sat at the center of lambda CDM as a fixed, unchanging number ever since, a cosmic setting, constant across every era. But if Riess is right, and DESI is right, that constant may not be constant. Dark energy may weaken, or strengthen, or shift direction across cosmic time. And if it does, the entire structure of the model bends around it. The expansion rate we measure locally is higher than the one predicted from the CMB, because between the beginning and now, the pressure driving space apart has changed. The universe you live in is not quite the universe Planck's map predicted, because the rules governing that expansion did not stay still while the light was traveling toward us. Notice what this does to the latter. Every rung was honest. Every star obeyed. The measurements were never wrong. They were reading a universe that was actually behaving differently than our theory told us to expect. The problem was never in the wood. It was always in the sky. Now separate what we actually know from what we hope. What we know, two independent, precise measurements of the expansion rate disagree at roughly 5 sigma, and JWST has closed the biggest escape hatch at 8. What we can infer with reasonable confidence. This is not going away as an error. What is a live scientific possibility? Dark energy is evolving, or an early burst reshaped the young cosmos, or something in the dark sector is interacting in ways we haven't caught. What is still speculation? Which of those explanations, if any, will survive the next decade of data from DESI, Euclid, and the Roman Space Telescope? What is off the table? Nobody has proven a hidden dimension, a parallel universe, or a broken law of physics. Riess himself has been careful about this. His warning is not that reality is collapsing. His warning is that our description of reality is missing a chapter, and we can no longer politely ignore it. Feel what that actually means for you, sitting where you are right now. The number that governs how fast space itself is stretching between the atoms in this room and the farthest galaxies we can see may not be a fundamental constant of nature. It may be a slowly changing quantity, writing on physics we haven't written down. Every future estimate of the age of the universe shifts a little. Every projection of its ending shifts a lot. If dark energy weakens over time, the terrifying Big Rip softens into something gentler and stranger. If it strengthens, the fate goes the other way. The end of everything is no longer a settled question. It is a live one, being rewritten by a telescope, watching a single pulsing star. Go back to that star for a moment. The Cepheid in NGC 5584, 72 million light-years from your eyes. It has been pulsing exactly the way Leavitt said it would, since long before there were humans to notice. James Webb watched it, and it did not lie, and it did not cheat. It gave its brightness honestly. It refused to save the model. Adam Riess spent 20 years building a ladder to that star to make sure the answer was clean. And when the answer came back, it was not the answer physics wanted. The star didn't break anything. The star was doing exactly what stars do. The break was in our confidence that we understood the space between us and it. That is the real weight of the phrase you saw in the title. Nobody found a portal. Nobody caught the universe cheating. What they found is that a model that has ruled cosmology for a quarter century may be a very good approximation to something larger and stranger. In the same way, Newton's gravity was a very good approximation to Einstein's. If you want to understand cosmology in your lifetime, this is the crack you watch. Watch DESI, watch Euclid, watch the next JWST data release. Because one question is still hanging in the vacuum, and it may be the most important one physics can ask right now. If dark energy is not constant, what quietly has been changing it all along?